Welcome back, AB Physics 1 students. Okay, so that was a really interesting video about Ørsted and this huge connection between electricity and magnetism. So, I keep saying electricity is over here and magnetism is over there. They're not the same thing, and yet he found this very strong connection that electricity creates magnetism, that moving charges create magnetic fields. But, we should have suspected that. Let's go back to our notes. We made this chart comparing all the fields, and we saw that anything that was in this column that creates a field is also the sort of thing that you use to test for it, that experiences the field. And so anything in this column belongs in this column, this column, this column, which means over here, if we saw that moving charges experience magnetic fields, well then definitely moving charges should create them as well. And so now we have this confirmation that moving charges certainly do create magnetic fields. In fact, all magnetic fields come from moving charges. It doesn't actually have to be a current, just any charges at all moving will create a magnetic field. So what are the implications of this? Well, while it was Ørsted who figured out the connection, it was Ampere who actually quantified it. So take a moment and write this stuff down. Okay, I'll describe a lot of this stuff, but I wanted to have in your notes. So here is a wire with current, and it's going to create a magnetic field for a closed loop path. Let's say we have some distance r away from the center of the wire, and we're going to draw a circle around it. So this sort of imaginary circle. You might recall back when we did Gauss's law, we drew like an imaginary surface around a charge. Well, now we're going to draw an imaginary circle around a wire with current. This is what's called an Amperian loop, named after Mr. Ampere, right? So Ampere's law says that if we add up all the little bits of length around this loop, it's going to give us information about the magnetic field. So this is just a little bit of the length, from here to here is a little bit of length, representing a tiny bit of length around the loop. And Ampere said if we sum up all the bits of the magnetic field surrounding this wire times the little bit of length around the loop, we're going to get something about the current. So this mu naught is this permeability of free space. It's just a constant. Don't worry about where it is just yet. We'll come back to it a little bit. So the idea is we want to sum up all these bits of delta L. So if I sum up delta L, delta L, delta L, delta L, all the way around the circle, I'm really going to get the entire length around the circle. That's known as circumference. Circumference is 2 pi r. Right? So now I draw a solid line here. It's not an imaginary loop anymore. Now it's going to represent the field line surrounding this wire with current. 2 pi r is just the circumference of the circle of radius r. And now we're just going to solve this for B, so it's mu naught I over 2 pi r. So this is now the equation for the magnetic field created by this wire with current. As always, let's define our terms here. So B is a magnetic field created by the current, specifically in a long straight wire. We're only going to do long straight wires. This equation is only for long straight wires. There are other geometries, but we're not really going to get to it in this course. As always, anytime we deal with a field equation, we must be very careful to know what it is that's creating it. So whatever current you put in here is the one creating the field. Now we're just going to really highlight that by reminding ourselves that current, the I is the current creating the magnetic field. If you go back to any of our field equations before, for electric field, for gravitational field, this is always the wording we used. Being very careful to define what is creating the field. R is the distance from the center of the wire, from the axis of the wire out to the location you're looking at. And then we get to mu naught. This is the permeability of free space. That phrase may sound familiar. Back when we did electrostatic effects, specifically with Gauss's law, we had epsilon naught. That was the permittivity of free space. How well a vacuum permits an electric field to exist. Well, this is the permeability of free space. This is how well a vacuum, or free space, allows a magnetic field to permeate its region there. And every material has its own permeability value. This is the vacuum permeability, or permeability of free space, and it's well known. Its value is given as 4 pi times 10 to the negative 7th Tesla meters per ampere. I know you probably knew that value anyway, right? No? Okay, well, while this number is not very intuitive, it's one of the really important numbers. We're going to box it in as if it were a new equation. Remember, I keep talking about there's only like 6 or 7 numbers that control our entire universe, and this is one of them. This is the one that controls magnetic effects. And if this number were any different, our entire existence would be different. That's pretty crazy. Now, the direction for magnetic field is another right-hand rule. We've done the right-hand rule for forces. Now it's going to be the right-hand rule for fields. And this is the way it works. You're going to grab the wire with your right hand, as shown here, so your thumb is pointing with the current. When you wrap your fingers around, it will show the direction of the field. So thumb in the direction of the conventional current. Wrap your fingers around to show the direction of the field surrounding the moving charges, the wire in this case, right? So you go ahead and try it like this person here. This person's giving you the thumbs up. You're going to get this right? So the charge is moving to the top of the page. And I like to do this with, rather than not use an imaginary wire, use your pencil or pen. So hold your pencil or pen in your left hand and then grab it with your right hand. So this way your thumb is pointing to the top of the page. You wrap your fingers around, and you should see your fingers are wrapping around in this way. If we're looking at it from above, this would be in a sort of a counterclockwise direction around the wire. That's the direction of the magnetic field produced by it. And if we go back to this picture here, it's the exact same idea. The charge moved to the top of the page, and so you grab your wire with your right hand, so your thumb is pointing at the top of the page, wrap your fingers around, and now you can see this is the general direction, sort of passing in front of the wire to the right, behind the wire to the left. Seen from above, this would be a counterclockwise direction for the magnetic field, again forming a continuous loop, just like our rules for magnetic field lines we showed before. Here's a photograph of a wire poking through like a piece of cardboard, and over here are some iron filings that orient themselves to the magnetic field. You can see they form sort of circular shapes around the wire. Here's another photograph. This wire has charges that are moving downwards into the page, or downward from our perspective, and they put compass needles around it. So here you grab the wire, go ahead and try it, with your thumb pointing to the bottom of the screen. You wrap your fingers around, you should be able to see that if you follow the red arrows of these compass needles, it would form this clockwise pointing circle. And that's what's happening here. The magnetic field line forms a circle around this wire pointing in a clockwise direction because now the charge is moving downwards. Let's try another example. In your notes, I want you to draw this wire. The charge is moving to the right. And go ahead and try to do the right hand rule. Go ahead and draw the magnetic field lines as a loop surrounding it. Here's a picture of that. So your thumb is pointing to the right, and again, use your pencil or pen in your left hand, grab it with your right hand, so your thumb is pointing to the right, and you should get these loops that point this way, sort of pointing to the bottom of the page in front, to the top of the page above. Each one of these loops goes around like this, and you draw a bunch of them, getting wider and wider, because the magnetic field gets weaker and weaker, and they do go all the way along the length of it. Now, drawing all these loops may be a little bit confusing, so let's see if we can practice doing this with dots and X's. So for this one, I want you to you've already drawn this in your notes. Put your pencil or pen right on the picture of your wire, on the paper. And then, using your right hand with your thumb pointing to the right, try to grab that wire. And feel free to turn your paper any way you want to, so you're not, twisting your wrist in an uncomfortable fashion and getting that carpal tunnel syndrome. When you do this, you should feel your fingers are hitting the page in this region below the wire, or towards the bottom of the page, right? If they're hitting the page, that means the field is pointing into the page, that location. So we draw some X's there. Now, take your pen or pencil, lift it up a little bit off the page, and wrap your fingers underneath, so that now you should see your fingers are sort of poking up through the paper over here. That means that the field is pointing towards you. Those are dots over here, right? So you physically feel your fingers hitting below the wire here, those X's. Your fingers are poking up out of the page. Those are dots. And then, you can, if you want to get a little more fancy, you can draw, well, first of all, let's label this capital B for magnetic field. But we can draw a couple more field lines here, and then maybe even farther apart. The farther we are from the wire, the weaker the field gets, right? Mu naught I over 2 pi r. By the same token, maybe draw some dots clustered over here, maybe farther away. I don't have room on my PowerPoint, right? Remember, the X's are the important parts and the dots are the important parts. The circles around it really just sort of highlight it. You don't really have to do that. All right, let's do a more complicated example. Let's have two wires. So in your notes, go ahead and draw these two wires separated by a distance r. They're both of length L. They both have currents pointing to the top of the page. We'll call this wire 1 and wire 2. So current 1 and current 2. Pause the video, draw this. Okay, so we're going to develop an equation to describe the force on wire 2. Now, why is wire 2 feeling a force? Well, it's because wire 1 is creating a field. We can draw a loop around it. You're going to grab this wire. Remember, anytime we're doing magnetic field, you're going to be grabbing the wire. So go ahead and grab the wire. You should see the field is pointing generally around this way, sort of away from you over here, towards you over here. We can draw X's over here, dots over here, and I'm drawing it this way so you can see that wire 2 is sitting in the magnetic field produced by wire 1. What's the equation for that field? Well, it's going to be, well, since it's B1, it's going to be B1 equals mu naught I over 2 pi r. We're calling it B1 because of the field produced by wire 1. Wire 2 does create a field, but if we're looking for the force on wire 2, an object can never experience its own field. I'm going to say that again. An object can never experience its own field. wire 2 is going to feel a force, but only because wire 1 is creating a field. So which current goes in here? Is it 1 or 2? It's 1, right? Remember, the field and the current go together. Remember, this equation, you might notice, looks an awful like our other field equations, like lowercase g equals capital G m over r squared. E equals kq over r squared. It's always the field is some constant times the object creating it divided by something with r. Here it's 2 pi r because remember it was the circumference of a circle, whereas before it was something with r squared because it was using Gauss's law for the surface area. But they all have the same format, and the object and the field go together. Okay, now we want to find the force on wire 2. What equation are we using? Is that QVB sine theta or ILB sine theta? Hopefully you recognize it's ILB sine theta, right? Now which current is this and which field is this? Here's where we have to be very careful. Remember, this is the field from some external force. That's B1. Which current is it? That's I2. Right? Because we're looking at the force on wire 2. So we take this field equation, we substitute it right in here for B is mu naught I1 over 2 pi r. Is the force on wire 2, so on the force on current 2. What's the angle theta? Well, here's where we see the charge moving to the top of the page. This field is pointing out of the page. What angle is that? That's 90 degrees. Sine 90 is 1, so it goes away. And then it's traditional to solve this for force per length. So we're going to move L to the bottom here. Collect some terms. So this is force per length equals mu naught I1 I2 over 2 pi r. We're going to go ahead and box it in. Now, why is it written as force per length? Well, look at this. When we write it as force per length, now this side looks like our other force equations, right? Constant, object, object over something with r is like G m1 m2 over r squared. K, q1 q2 over r squared, right? So it's constant times the two objects creating it divided by something with r, and then, you know, most times you want to find the force, so you just automatically put the L over to the other side, but this at least looks like the other equations. So this will get us the magnitude of the force per length of wire 1 acting on wire 2. What about the direction? Well, we now know that there's a charge moving to the top of the page. The field is out of the page. Go ahead and do your right-hand rule and figure out the direction of the force on this one. Okay, now be careful. Which right-hand rule is this? Is this the pointing one or the grabbing one? You've got to know both of those. Yeah, this is the pointing one, right? The pointing one is always for forces. The grabbing one is for fields. We've already got the direction of the field. We want the force on wire 2. So our pointer finger points to the top of the page. The field is out of the page. We should be getting our thumb pointing to the right. This wire will feel force to the right. Okay, so what about the force on wire 1, right? Wire 2 is going to create a field. Wire 1 is going to experience that field. Go ahead and pause the video and figure out the direction of the force on wire 1 because of wire 2's field. So there's the long way and the short way. The long way is saying, well, wire 2 creates a field, so sort of forget about this circle here, draw a circle around wire 2, or grab wire 2. You should feel there's your fingers hitting the page over here, so the field from wire 2 is pointing into the page. Wire 1 has charges moving to the top of the page, so now we do the pointing. Our pointer finger points to the top of the page, the field is into the page, our thumb should be pointing to the left. That's the long way. What's the short way? Well, here we have two objects exerting forces on each other. We know those forces have to be equal and opposite. Of course, it's Newton's third law. If wire 1 causes wire 2 to feel a force to the right, wire 2 had better cause a force on wire 1 to the left. They apply equal and opposite forces to each other.